Distributed storage is a very reliable storage, but for some reason I avoided Ceph for a very long time, and this changes today. So, because I avoided Ceph for, well, really forever in my life, and I never had a chance to really properly get to know this technology, even though I was using it already kinda in Proxmox clusters and so on, but I wanted to do this from the very scratch, from the beginning, to learn how this really works. This won't be really that deep, however, because I will be using Rook Ceph Helm chart in order to install Ceph into my Kubernetes cluster. And this makes things a lot easier. And before we go any deeper, we should know at least some very basics of the Ceph itself. So Ceph is made from multiple components that are, well, obviously needed for Ceph to work properly. First of those will be Ceph monitors. It really maintains cluster state and quorum. So it is very important to keep monitors in a quorum, which really means that you probably want to have at least 3 monitors in that case, or maybe 5. There is also Ceph Manager component, which provides monitoring and management functionalities really. So you can talk to the Ceph Manager via REST API or via the dashboard in your web browser if you want to. It works alongside the monitors to enhance observability. So those two are the essential components to actually have anything working in your Ceph. If those are down, then you might have a bigger problem. And then when you want to actually store the data, the core storage layer for Ceph is Rados, that allows to provide object-based storage interface to all your data. So really what happens here is that your data is chunked into smaller objects placed onto different disks through the whole cluster. Rados is not something you can really use directly. To be able to actually store the data, you will need Ceph OSD, and they will actually take care of placing data into the specific disks, and each OSD corresponds to a single storage device. OSDs handle replication, recovery, rebalancing, so it's a core component of the Ceph itself. Okay, so we have OSDs, we have manager, we have monitor, but we still cannot place any data. That's because we need to create clients that are applications that will interact with the Ceph storage through different interfaces. The first will be RBD, and it provides, well, really block device that can be used for OpenStack, for Kubernetes, Proxmox, and so on, whatever you want to use it. Next Ceph client we want to talk about is a CephFS, which is POSIX compliant distributed file system. It's quite great because you can actually spread your small files across the whole cluster, mount it very similar to mounting NFS or maybe Samba if you prefer, and just accessing those files. So it's a great way to make highly available file system thanks to that. There's also third client that is very worth mentioning, though we won't be working with it today. It's Rados Gateway, which provides S3 compatible object storage API. And I will be leveraging this later, and I will migrate my data from Garage to Ceph and migrate my GitLab and my Grafana data later on. So let's install Ceph. As you can see already, on my left side on the screen I have my Kubernetes launch command, which allows me to see what's going on in my Ceph installation in almost real time, and I have also my terminal when I will work. I already installed my Rook Ceph operator. You have to do this first in order to be able to install Ceph components. I already prepared a few files for me, so when we look at vim rook ceph and cluster.yaml, you can find out right there that I already created my Ceph cluster. You can see that this file is very complicated, but actually I just took this directly from the documentation, from the examples, and I just modified a few things. So things I really modified here is when we go slightly down, you can find out that I have my Prometheus endpoint created, so I can gather statistics from my Ceph cluster. Monitoring is enabled thanks to that. When we go to network section, I also enabled compression. This is on-wire compression, this is not data compression at this point. Other things that you will probably want to verify is actual storage configuration right there. So what you can do is you can just give Rook Ceph access to all your disks, say use all nodes, use all devices, and it will just find any empty storage device. It will just create OSD that will use this storage device. But if you don't want to do that automatically, you can always create filters with a regular expression or just specifying devices by themselves, and this will limit your storage devices to exactly what you need. If you have any data already created on that disk, it will not create OSD for that disk. It will just refuse to work with that disk at all. It will say that it's not available to be used. So keep that in mind. If that happens during Ceph Rook installation, you will need to add that disk manually later. It won't be detected after all and added automatically later. And here you can also set how many OSDs per device you will have. If you really want, you can actually specify all the nodes with all their specific disks. So if you have really weird cluster with really weird computers, and I know that homelab people might have something like that, you just grab whatever you have on your shelf, or maybe some older computers, some weird hard disks that you have. In that case, you can specify each node and each disk individually if that's the case, so don't be worried. So with all that config in mind, let's finally install Ceph cluster. To do this, I will just run kubectl apply -f rook ceph cluster.yaml you just saw earlier, and Rook Ceph operator will create a monitor, will create managers, will create crash collector also, and it will create all the OSDs that should be automatically detected by those Rook Discover pods right there. Okay, about a minute later or so, we finally see a cluster created successfully message. So that's great, it means our cluster is working perfectly fine. If you want to be sure, then you can run Kubernetes Rook Ceph status. Here I have Rook Ceph plugin installed to my kubectl, so keep that in mind. But on the left you can see that we have a few OSDs already. So this is great because it means we can now use those. Well, almost, not really, because we still don't have any pools created. You can list all your pools that you already have created by using Ceph OSD ls pools. And as you can see, we have only one pool already, .mgr. This is internal pool, don't touch it, because the manager creates internal data for itself in this pool. But we still have to create pools for ourselves in order to use those. Let's look at this, what I already have. And you can see that I have my Ceph block pool. I am specifying that I want this to be replicated in 2 copies. So when we're talking about, let's say, 10 GB video file, some part of that video file will be on servers 1 and 2, some part of that video will be on servers 2 and 3, and the third part will be on servers 1 and 3. That's of course assuming you have only 1 disk per server, because in my case I have 2, which means that the data will be spread across those disks. I am also enabling compression because, well, it's a home lab and I don't have much money to buy NVMe drives, so I am using as much compression as I can in order to utilize as much space as I can. And as in Kubernetes fashion, you always have to specify storage class in order to use this in persistent volume claims. So in this case, I just need to specify my cluster ID, which is the namespace where the cluster is installed. It's Rook Ceph by default, and my pool name, which I just had that right there on top. The rest stuff is just taken from documentation, from examples of the Rook Ceph. I just copied and pasted this and it works. Okay, back to topic. As earlier, we will just create all those objects, which is 2. I will just run kubectl apply, and on the left side you will see that my Ceph block pool is getting created right there. It was very fast, it already says it's ready. And we can verify this very easily by using ls pools command once again. So as you can see, I have storage block data right there, exactly how I named it, and I can use this. Let's verify the storage classes I have. As you can see, I have my Ceph block, and when I want to use this, I can just very simply say, hey, use the storage class. I want to use my Ceph block, so CSI provisioner will talk to Ceph and ask Ceph to create a volume on that pool and attach that volume into my pod. And I can just format the file system to ext4 or XFS or whatever you want in Kubernetes and use that as my storage for MySQL or Postgres or whatever you want to store on that storage. And all of that is great, but we still have one more thing to do, because we would like to install also CephFS. Because right now we just have block storage, we don't have file system yet. But file system is very easy to create, it's almost the same. So let's see this CephFS configuration. It's not much different from what we saw earlier with the RBD in the block configuration. But what's different here is that instead of creating one pool, you have to create at least two pools, one for the metadata itself and another or more than one for the data. In this example, I have metadata as regular replication with the size of 2, and data pools I have only one with the size of 2 replication type. But I was also testing Azure coding. It saves a lot of disk space, but unfortunately it's absolutely terrible in performance. Given it's Kubernetes, again we have to provide storage class, and it's again the same. Just one difference is that for the pool you have to provide the name of that one of pools that you created right there. If you have more pools, you have to create multiple storage classes, and in the FS name, this is the name of the CRD itself. So let's apply this. And again, operator does its job, creating our file system. And there it is. As you can see, the storage FS is ready, which means we can use it now. How we can use it? Of course, via storage classes. First, let's verify our pools. So you can see we have our block data we created earlier with RBD, and we have also 2 pools for the CephFS. We can also verify all of that by using kubectl get storage class, and you can see that storage classes are configured right there. So since everything works fine, what we would like to do as a last thing is install WordPress, because it's a great example. Everyone knows WordPress. It needs MySQL database, so MySQL database is something that works on a block storage, and also WordPress itself saves files to file system. All the uploads or the themes that you can upload, all the photos are stored on the file system, so CephFS will be great for that. I already created my WordPress configuration file earlier, so let's take a look at this. As you can see, I'm setting persistent to my CephFS storage, and MariaDB is using Ceph RBD in that case. Keep in mind, those are names of storage classes, not name of the Ceph pools. Let's apply this, but before we do this, I wanna watch what's happening right there. So let me switch to another namespace. And let's install WordPress into that namespace. And it's done. My WordPress is installed. Both pods for MariaDB and WordPress itself are ready and running. So all we have to do now is just open the web page, wp test, and my website is working perfectly fine. Let's try to log in into wp admin. So we need to find out the username and password, but fortunately our Helm chart actually shows us this information. The username is user, very easy, and the password is something we have to find out on our own from Kubernetes secrets. So I'll just grab this, copy and paste, and click login. As you can see, it works perfectly fine. I can see all my posts, edit those. It works flawlessly. It generates quite fast actually. I'm pleasantly surprised with how fast CephFS it is, at least for the read side. And by the way, I can scale this very easily. Just by running scale command and specify, let's say, 3 replicas of my WordPress deployment, I can run this with multiple replicas on multiple nodes thanks to CephFS, because now each of those pods will mount a file system. This is not possible with the block devices, so I can't scale MariaDB, for example, like that, otherwise my data will break. But with CephFS, I can do that at least with my WordPress and PHP application. In terms of Ceph performance, I did some benchmarks, and while being far slower than native NVMe disks, obviously, it's still very good in terms of read performance. Regardless if you're using replicated 2 or using replicated 3, using compressed or uncompressed, it's okay. But in terms of actual top tier performance, the best would be replicated 2 compressed. So actually all that data was compressed on my disks and it was faster to get. So depending if you have money for CPUs or money for disks, you choose one or the another. In terms of write performance, Ceph is not that great, unfortunately. If you wanna have very low latency database, it's not really possible. Probably you want to look for some enterprise solutions like NetApp and CephFS. For regular use and regular VMs, it's perfectly fine though. Just keep in mind, we are still talking about replicated volumes. Because when we start talking about erasure coding, it's totally different story. It's absolutely, utterly terrible, don't use this. It's okay only in sequential reads and sequential writes, it's also surprisingly okay, but anything random, it's crushed, it's absolutely crushed. Don't use this for any random access use cases, really. Thanks for watching my journey to Ceph. If you found out any mistakes, please leave a comment below to tell me how I screwed up. If you found this interesting, hit subscribe also down below, so I can produce more interesting videos and be helpful to you with more maybe tutorials in future.